So the next part of the Kyber dilithium is furthermore the correct implementation of these algorithms require precise technical knowledge. Their improper use, especially in the generation of randomness or in manipulation of error and random renormalization, can create the vulnerabilities. Therefore, the use of well-audited libraries and adherence to secure implementation guidelines is essential to secure the resistance promised by the theoretical design. Together, Kyber and the dilithium present as a robust, practical, and stable response to the challenge of replacing classical cryptographic system in the face of quantum threat. Their strengths make them ideal candidate for general applications, from secure web connections TLS to software signature, digital identities, VPNs, IoTs devices, and real-time authentication systems. Their selection by the NIST as the first post-quantum standard marks the beginning of transition that is already underway and will permanently change the architecture of digital security. Practical implementations. The transition to post-quantum cryptography is not a theoretical project relegated the academic laboratories. On the contrary, we are witnesses and a progressive and deliberated adoption by key players in the global digital ecosystem who have already begun to integrate algorithms such as Kyber and dilithium into real system. This early adoption is based on strategic need to anticipate the threat whose consequences, if ignored, would be crucial for confidentiality, integrity, and authenticity of digital information is in the medium and long term. The algorithm selected by NIST, Kyber for key exchange and dilithium for digital signatures, have already been implemented in multiple open source cryptographic libraries facilities their integration into existence application and system. One of the most notable is LIBOQS, Open Quantum Safe, a collaborative project that provides efficient implementation of post-quantum algorithms and integrated into them into widely used tools such as OpenSSL. Through LIBOQS, developers and organizations can experiment with the Kyber, dilithium, and the other candidates in real-world context, including network protocols such as TLS, SSH, and VPNs. Support for post-quantum cryptography has also begun to appear in browsers. The test web browsers, Google for example, conducted an experiment in 2019 with modified versions of Chrome that used the hybrid scheme based on X25519 classic and CECPQ2, a variant of Kyber during TLS key establishment. These types of pilot tests have allowed us to observe the real impact on performance, compatibility, and security, laying the groundwork for wider adoption. Microsoft, Cloudflare, and AWS have followed similar paths, running tests with hybrid TLS that combines a classic and post-quantum algorithm in key negotiation. So that even if one were compromised, security would still be valid for the other. In the field of critical and government infrastructure, decisive steps are also being taken. The NSA, US National Security Agency, has published guidelines for migration to quantum resistant algorithms, explicitly recommended to use of the standard selected by NIST. The Europe bodies such as ENISA, European Union Agency for Cybersecurity, and projects funded by the Horizon Europe program are developing guidelines and frameworks to facilitate the adoption of these new technologies in public administrations. critical infrastructures operators, and defense and entity regulated by GDPR. If in the private sector, companies such as IBM, Intel, Cisco, Thales, X, NXP, the Gemalto, Amazon, Qualcomm are incorporating post quantum support into their products, whether at the level of secure hardware, cryptographic modules, smart cards, or cloud services. These players recognize that in addition to being a future requirement, post quantum cryptography is becoming a competitive differentiator. Being able to offer quantum ready solutions gives an advantage in tenders, audits, and markets sensitive to cybersecurity. A notable example is the use of Kyber dilithium in Internet on Things devices embedded system environment where power, memory, and process limitations pose particular challenges. Thanks to their module design, optimization versions, and relatively low power consumption, both algorithms have proven viable even on mid-range and low-end microcontrollers. Industry research projects have successfully implemented Kyber on devices with less than 32 KB of RAM without compromising functionality or security. This opened the floor to its integration into millions of sensors, actuators, and connected devices that require long-term security. The field of digital signature has also begun to incorporate dilithium in environments where verification longevity is critical. In applications such as software signing, digital certificates, electronic identity, and legal files, it is not enough for the signature to be secure today. It must remain very variable in 10, 20, or 30 years. If in the context dilithium is a positioned as a robust and auditable solution, ideal, ensuring traceability and legal validity in the quantum future. The last page is that beyond one of trade adoption, one of adoption, what is happening in the construction of the ecosystem of tools, documentation, and standards that will facilitate the transition on global scale. Organizations such as the IETF, Internet Engineering Task Force, are actively working on defining secure protocol for the use of post-quantum cryptography on the internet, including proposals such as PQTLS, PQX.509, and PQVPN. These initiatives see not only the define how to use the new algorithms, but also ensure their interoperability, compatibility, and secure in heterogeneous systems. However, challenges remain. The management of larger keys, adoption of legacy infrastructure, legal validation of new signatures, and training of professionals are critical issues that must be addressed with careful planning. Mechanism for hybrid transactions must also be developed to maintain compatibility with classic system while the new post quantum layer is developed. The gradual approach is key to minimize risks, avoiding disruptions, and gaining time to adopt regularity and normative standards. In short, Kyber and dilithium are already leaving the laboratory and entering reality. Their implementation is in libraries, commercial products, regulated environment, and emerging standard marks a turning point in history of cryptography. It is not just a matter of being prepared for an uncertain future, but of building a secure infrastructure today that is capable of withstanding the technological challenges of coming decades. In the following chapters, we will discuss migration strategies, hybrid system design principles, and the best practices for integrating these new algorithms into production system in a secure, effective, and sustainable manner. Thank you very much.